Hello, everybody. Hello in the lecture hall. Hello, people on Zoom. So today is special. It's the last lecture. So we are going to go through what we have been doing during the semester on the very high level. There will be no new material. Just to give a bit of perspective, zoom out and look at the big picture. Then I'll say a few words, of course, about the exam. And in the second hour, we'll have this big quiz with everybody, both on Zoom, in the lecture hall. Hopefully, a few more TAs will join us. And we'll have this game played between you, the students, and the TA team. All right, so let's get started. So I'd like to start with this list of 10 principles of big data that I've already told you about. In the middle of the semester, if you remember, I think it was roughly when we were done with HDFS and we were looking into H-based, these white column stores. So I'd like to go again through this list of the 10 high-level principles, now with having in mind everything that we've been doing during the semester. So the first principle is called learn from the past. And this is actually almost a lesson of life. It's not just about this lecture, but it applies in particular to databases. And the example that I like to give in here is the fact that, for example, tables are thousands of years old. If you remember these clay tablet accounting tables, they basically have existed for a very, very long time. We have data shapes, tables, trees, cubes, graphs, and text. And the data shapes are extremely important because this is going to decide on the productivity and performance of your system. If you pick the wrong shape and you fit the wrong data, so you fit data with a certain shape into a database system that has a different shape, then it's going to be slow. Right? So just being aware of that is going to help. The other thing I want to say about learning from the past is actually the lecture of what's going on right now with XML and JSON. Because XML has been around roughly for, I would say, 24 years, now maybe soon 25. XML is a very mature ecosystem. It has the language, it is specified, it took a lot of effort to do it. It has a schema language, it has a linking language, a pointer language, which is out of the scope of the lecture. We have a query language called xquery and so on. So it's an ecosystem that is very stable. It is actually widely used in many companies. An example, for example, of latest developments is the electronic tax documents from the banks that are now in XML. And that way the tax office can directly process these documents electronically. It's basically an XML document embedded in a QR code. Another development is these reporting taxonomies that are establishing themselves in the country after country. So in the US, for example, all public companies are required to file their financial reports to the Securities and Exchange Commission in an XML-based format. It's called XBRL, but it's XML-based. Right now, there's new sustainability reports that are also making their ways with a new board and it's ongoing standardization. So XML is actually a thing. But somehow what happens is that JSON appeared, and JSON was meant to be simple, and JSON is great. You know, I love JSON. JSON is great. But what happened is that in the early days of JSON, there was a bit of aversion for XML. You know, XML is too complex. We don't want to hear about XML. Let's not just do what XML did and do our own thing. And what has actually happened in the subsequent years is that they have been doing exactly the same mistakes that the XML people did before. Basically, we say, okay, we don't need a schema. Oh, maybe after all, we need a schema. Oh, we don't need a query language. Oh, maybe after all, we do need a query language. And if only from the very beginning, the JSON community had learned from the XML community, the entire JSON stack today would be even more mature than it is. Of course, it's slowly going on, but we would have gained a few years. If we had looked at what others have been doing. So this is what I want to say from the database perspective. Okay, so number two is keep the design simple. So this is this idea that in order to massively scale, we saw a lot of key value models all over the lecture. It's everywhere. a JSON object is the key value model. In HBase, we have the key value model. In HDFS, when we have the block IDs and the blocks, or when we have the file names and the list of the blocks, the key value model is everywhere. It's extremely simple. It's gates, and this is the secret to a large system, and this is something we love in computer science. We like simple things. So keeping the design simple helps a lot, and there is this quote by Einstein that I like. Everything should be made as simple as possible, but not simple, of course. That's the art of doing it right. Third, modularization of the architecture. It's something that is absolutely crucial in computer science. Whenever we build computer systems, we like to separate into layers, and different people deal with different layers. And at every layer, we just design the communication that we call southbound. So this is basically let's take the orange one. There's the southbound API that communicates with the lower layer, and then the northbound API that communicates with the north. And this modularization simplifies a lot of things. It's like when you build a house, there's the electrician, the plumber, and so on and so on. Right? So you separate the concern. This is exactly what we've been doing in the lecture, where we had all of these components that a lot of systems have. Right? There is an overall paradigm. There's the data shape, basically, and there's the data model. There is a syntax. There is a query language, there is an architecture, there is the mapping to other shapes. So all of that gives us the modularity. And if you look at the different shapes, so for example, it's like, this saying that if you have a hammer, everything in the world looks like a nail, right? And so there are these 5 shapes: cubes, tables, trees, graphs, and a bunch of text. And every time, if you see the data as one of these 5 shapes, the vocabulary you're going to use is going to be different. If you have a table, this is familiar to you, right? You select, you project, you group, you join, you sort. And if you have trees, this is what we did with JSON and XML. You look up, you navigate, you normalize, denormalize. We've seen that, right, with the normal forms. You validate and so on. And then, of course, there's what's outside of this lecture. So I do it for the computer scientists because it's it's a longer lecture. So we can also have graph like data where we can traverse the graph, we can find patterns. We have data cubes. This one is covered in information systems for engineers. So this one is in full. We slice cubes, dice. It's a bit like a Rubik's Cube, right? We can roll up, cross-tabulate, pivot. So it's also a different operation, very popular in business analytics. And when it's text, so this is called information retrieval. You can also do things on a simple level, like filter, map, group, and aggregate with MapReduce, but there's also a cool standard inverted index way of doing things. But again, this is outside of the scope of this lecture. In this lecture, this is where we focused our effort: tables and trees, knowing that trees are denormalized tables. In terms of syntax, we saw that CSV is ideal for tables, and for trees, we have XML and JSON, but we saw, there's others. Parquet and Avro require a schema, so they are more compact than XML or JSON, but they are binary, so very highly recommended. Yes?
Does it make sense to store a table in a Parquet format?
Does it make sense to store a table in the Parquet format? Yes, absolutely. It makes sense. It's going to be more compact than CSV. You're just going to not use all of Parquet's features because Parquet can also store nested tables, so you would just not use that. But absolutely, it makes perfect sense. You could use Parquet. Basically, what you would have is a data lake version of your relational database. But by default, the first thing that should always come to your mind if the data looks like a table is a good old relational database. If you don't have so much data, like you have megabytes, gigabytes, and so on, you should really try with PostgreSQL first. And then you need a good reason, basically, to go outside of that. But yes, absolutely. I will actually say a few words about going from shape to shape, because that's a very fundamental aspect. For cubes, I mentioned XBRL. It's XML-based, but it allows you to store data cubes. For graph, there's an XML dialect called RDF over XML. There's another one called Turtle, and so on. But again, this is not part of our lecture, right? This and this is outside of the scope. This is what we looked at. And text, of course, is as is. In terms of query languages, we looked into SQL for tables and JSONic for trees. But for trees, there's actually many others. I'll come back to that. For graphs, we have Sparkle, Cyber, GraphQL, and so on. Bunch of text, it's typically your own code. You can use MapReduce, Spark, Python also. MDX is for multidimensional expressions, that's for data cubes. So you see there's a whole ecosystem. This is why it's so important to know what shape you have so that you pick the right language, right? Otherwise, you're going to run into issues. It's going to be impractical, it's going to be slow. All right, and I'll come back to all these languages right there. I have a few words to say about that, and I also come back on this Parquet versus stable thing. All right. We also saw that we like to have homogeneity in the large, in the sense that if we zoom out, we love to have billions or trillions of the same thing. We love that in big data. We love linearity. This is what we call linear behavior, right? So this is what when we scale out. So we love homogeneity in the large. This is what allows us to scale so much, because the reason, the driver, is that the capacity has increased enormously, but the speed at which we can read it, not so much. And the latency, the time you need to wait to receive the data, it's even worse. Right? So the consequence of that is that we need to scale out, and in order to do that, we need to have homogeneity in the large, right? Trillions of similar things. But of course, if you zoom in, there is a lot of diversity in these similar things, because then suddenly you see that all the individual records or the individual items in your sequence, if you're in JSONic, or the individual rows in your table and so on, in big data might not look all alike. You might have additional types, missing types, mismatching types, and so on and so on. This is just real life, because when you accumulate logs over 20 years, the schema might change and so on. So this is why in the small, we have heterogeneity. And big data is the two together. It's trillions of similar looking things, but when you zoom in, you see that there's actually finer levels of detail. In order to deal with these specific details, of course, you need types. Types are not new. We had them in relational databases as well. And this is actually by request of one of your colleagues, I think 1 year ago, who asked, can we please have a correspondence table with, all of the types across all the various technologies? So I already showed you, I think, that slide in the data modeling lecture. What is important on that slide? What's important is just to realize that no matter what technology you look at, JSON schema, XML schema, Spark SQL, PostgreSQL 5, it's just the same. It's always the same. Maybe it's a different name, just like Swiss German dialects, right? But in the end, you'll always see more or less the same types. Right? So you need to look up the documentation whenever you learn a new technology to know exactly what types they have. Maybe they don't have all of them and so on. But more or less, if you know one of them, then you can learn any other very easily, because then you just get how it works. Right? All right. Then what we do is that we abstract it every week, a logical model from the that we separated from the physical implementation. This is why every week, instead of directly telling you how a system is implemented, I started with the modeling, the high-level thing. For example, when I explained to you HDFS, I started telling to you, okay, there's a hierarchy of files organized in directories. Every file is split into blocks, and that's it. That's the model. That's the logical model. And then that separates, we separated it from the implementation, where you have the name node, the data node, and all these details of the way this is done. But this is just a physical detail, right? What's important is that we separated the logical level from the physical implementation. This is tied with the modularity. This is what allows us to have the modularity, because every physical implementation is actually the logical model of the layer below. And every logical model is the physical implementation of the layer above, right? So you see everything is relative in your technology stack. Which is why, and now I'm coming back to the question you asked, like, can we store tables in Parquet? The answer is yes. What you are actually doing when you store a table in Parquet is that you convert from a model that is tabular to a model that is arborescent trees. So it is possible to map from a model to a model, from a shape to a shape. And so in the case of storing table in Parquet, we would be exactly if we. So these are the easy ones, right? A cube can easily be stored as a table. We did it in information systems for engineers. A table can easily be stored as, so I say a tree here. But as you know, I mean a collection of trees, right? We've done it enough. So it's collections of trees. So a table is a collection of rows. Rows are flat trees. So in particular, you can store tables as trees. Trees can easily be stored as graph because it's just that graphs have cycles and trees do not. So a tree is always a graph. A graph can also always be stored as a table. You just have one edge of the graph per row. This is out of the scope of the lecture. So basically, you can convert one shape to the other. What does it mean? It means that technically, you can, if you want, implement a relational database on top of MongoDB. Or you can implement a graph database on top of PostgreSQL, right? You can take any system and implement any other system on top, but of course, it requires a lot of engineering. So you can convert, it's kind of an equivalence, just like we say that all the programming languages are equivalent. In a way, all of the data shapes are also equivalent. You can always convert one to another. All right, so we have this architecture with all of the layers that has the storage layer, then on top we process data with MapReduce, Spark, and so on. And then we have this fancy declarative language with which we can manipulate the whole thing. All right, so this I showed you before that we have the assembly code. So this is very, very specific to even computer scientists no longer program that way anymore today, or very few at least. We have imperative languages, so this also includes Python. And then we have the functional and declarative languages. This is where SQL and JSONic are. Then we have something that actually appeared later. Strangely, it was the opposite direction from here. It's what I call the proto-declarative languages. This is basically PySpark, Spark transformations, data frames API, pandas, and so on. I call them proto-declarative languages because they are not as high level as SQL or JSONic. And then we have the same evolution in machine learning, where we have now libraries. Most of them are in here, like TensorFlow, PyTorch, and so on and so on. But in the future, I expect we'll also have high-level machine learning languages, just like SQL and JSON, right? This is on the way, it's going to take time. So this is it. And of course, we focused this lecture on both the lower level paradigms, like Spark, MapReduce, and so on, and the higher level languages like SQL and JSONic, knowing that these are implemented on top of these, right? It goes hand in hand. All right, so we have this RumbleDB project that was actually started as a master's thesis. Now it's 5 years ago, and there's probably 15 to 20 students who have been working on it since then. So it's something you can actually use outside of the lecture for projects, in semester projects, master's thesis, if you want to query your data. So feel free to do it. We'll also have it at the exam for practical exercises, but I'll tell you more about that. All right, then we saw that that's the seventh principle. We like to shard the data. Sharding the data means that when we have trillions or quadrillions of items or of records or of rows or of trees, we like to partition it and put like 1 million here, 1 million here, 1 million here, just spread it all over the cluster. This is something that is very natural, and it almost happened every week. We did it with AGFS, with Spark, with MongoDB. We saw that we were also sharding and so on. So we almost always shard at large scales. The twin sister or brother of sharding is the replication. We also love to replicate data because we don't want to lose it. In AGFS, we have 3 replicas by default of every block, just in case the system fails, right? So we love to replicate the data in a big data setup. So sharding and replicating goes hand in hand. One is horizontal, the other one is vertical. 9, we build a lot of cheap hardware. I hope that this is one of the things you learned in this lecture, if you didn't already know, that in a data center, it's really just a lot of cheap hardware. This is really what it is. So you have tens of thousands of cheap computers that are just piled up in racks on top of each other, consuming, of course, a lot of energy. which is the reason why it's hard to scale beyond the hundreds, thousand machines in the same data center. But basically, we demystify data centers and saw that this is how things actually work. We saw that the architecture is very often, oh, why did I put decentralized? I mean centralized. So it's a centralized architecture. For example, the name node and the data nodes, the HMaster and the region servers, and so on and so on. So very often it works like this, that one node coordinates the whole cluster, and the other nodes take care of storing the partitions of the data, working on the partitions of the data. So this here is where you have the shards all over these machines here, and then you work in parallel. And finally, the batch processing is just as important as parallelism. This here, the batch processing, is to avoid if your tasks are too small. The task in MapReduce or Spark is the amount of data you process, like an assignment on a subset of the input. If your tasks are too small, then your system will spend almost all the time waiting for a task to begin. You just spend the entire time triggering tasks. So you need to find the sweet spot in the size of a task such that you don't spend too much time waiting for the tasks to be started. This is called batch processing. It's the idea that instead of processing one record at a time, you process maybe 10,000 records at a time or 100,000 records at a time. And these are called batches. And we saw that also for storing data in HBase, we also store in batches the way that, with these log structured merge trees, that we keep the updates pending in memory. We wait until they accumulated, and then in a single batch, we write down to the disk all the changes we made and propagate to larger and larger files. Okay, so there's a few design choices that you're going to face in the future with big data. So you will have to learn to use existing products. But in this lecture, normally I equipped you with enough theory and knowledge for you to very easily learn any new products. The principles are the same, really. So if you look at the documentation, maybe the names will change, a few things will be different, but you'll see it's going to be quite easy to learn new products. A consequence of that, before learning a new product, is also to choose which one to use. And here too, you should have enough knowledge to know what the different pieces of the entire technology stack are, so that you can make informed decisions. And in particular, if you know now about the data shapes, is your data like tables, is it like trees, is it like graphs, and so on, then you can pick the appropriate product. Another dimension for picking the appropriate product is, remember, ETL versus data lakes. There are systems like MongoDB or PostgreSQL where you have to import the data, but then you have plenty of bells and whistles like indices, faster queries, updates, and so on. Or you can prefer to have a data lake with S3, HDFS, and Spark, and so on. Then you're going to be slower, but you don't need to populate, you don't need to import the data, right? So it's a compromise to make between the two. All right, and finally, but this is maybe more for computer scientists, even though maybe some of you will be involved in projects later, is that maybe you realize that none of the existing products of the market actually does what you're looking for. And what you do in this case is that you just design a new one. But again, to design a new one, you learn the lessons from the past, you see what other people have been doing, you learn from their mistakes, and then you build a brand new product that takes it to the next level. All right? So you have to ask yourself, what's the shape of my data? How much data do I need to store? If it's only a megabyte of data, don't go to a data center. Use your laptop. That's more than enough. In fact, in 90% of the use cases, and here I'm also thinking of startups, startup founders, and so on, a laptop is enough. In 90% of the cases, you just need to write code that is efficient enough to make it work on your laptop, but only in a few cases do you really need a cluster. And you can save a lot of money at the beginning of a startup by being aware of these things. Then what do you want to do with your data? Do you want to read it? Do you want to update it? That also influences the choice of the design. And most importantly, when you want to invent new things, ask yourself, do you really, really, really need to reinvent the wheel? Because again, people do that all the time. They don't realize that something has already been done. And that's a shame because, you know, they lose resources, they lose money, while they could directly reuse something that already exists. Right. So this requires this critical thinking that we love at ETH to transmit. And this approach that I told you about, you know, you can only have a second computer once you've shown you know how to use the first one. Do not underestimate your laptop. Some of you have your laptops with you here. A laptop is extremely powerful in 2022. And again, there's a lot of things your laptop can do, and a lot of people underestimate that, what you can get out of it. All right. So this is a reminder that yes, big data is about this discrepancy between capacity, throughput, and latency that I told you about. And I hope that by now you are convinced that this is really the source of the problem that big data is solving. And this is why we have parallelism, and this is why we have batch processing. All right. So by now we've seen that we can convert tables to collections of trees, which is the denormalization. We go to heterogeneous data sets and nested data sets. We've seen that when we have collections of trees, we can scale out to plenty of machines by sharding and by replicating. We've seen that we can also postpone the validation of the data, meaning we can throw the data on the data lake without bothering whether it's messy or not messy and so on, and we validate later. And when you validate, this is when you can convert your data to Parquet, Avro, and so on, and then accelerate the speed of your queries. And then you can also use, when it's valid, some query languages that will understand that they both work with validated or not validated data. But basically, you have plenty of technologies that work well together. All right. So this is what we've done, right? And now we need to look at the future. What's going to happen in the future? What I think, this is actually something ongoing, is that technologies that, like MapReduce or Spark, ultimately will disappear from the sight of everybody. It's like, you know, 20 years ago or 30 years ago, a lot of people would build their own computers. We would buy the spare components and build our own tower and install everything yourself. Now it's a bit less popular. You know, you just directly buy a fancy phone, smartphone, or computer, and so on. And today it's a bit what's happening. A lot of people enjoy using the Pandas API and the Spark and the PySpark and so on and so on. But I think in the future, this will not stay. People will slowly move to these higher languages, just like SQL, JSON query, and so on. So MapReduce and Spark will still be here, but in the background for the actual data processing. This implies that people understand the logical level and the importance of data shapes, trees, tables, graphs, cubes, text, that basically is really the center of everything. That's really the first question, and I keep repeating that, I know, but this is really the first question that you have to ask yourself whenever you need to process data. There is ongoing work and several people working on a grand unification of data shapes, a little bit like in physics. You know, we try to unify all the forces, electromagnetic, strong wind, and so on. The same goes for data. Some people dream of, it's called polystore, for example, if you need a central database that supports all of the shapes under the same paradigm and language. So some people are working on that. Of course, here the challenge is the standardization of that when this is done. So the W3C is one of the places where people actually need to try to standardize things, but there are also other places. This is mostly web related. What I like to show about the standards, so I'm going back to all of these languages that I told you about, you know, JSON query and so on. You know XKCD, right? I'm sure you do. Okay. All right. So this is an XKCD. So the situation is there's 14 competing standards. So in the case of the query languages, this is pretty much what it is. And then somebody realizes, okay, we need to unify them. And then they come up, this is really reality. Every couple of days, I see an announcement by a company with a fancy new website that we have discovered that we need a query language for JSON. And here is our proposal of a query language for JSON with a fancy website, except that what really happened was that there is just one more language. So I would say 12 years ago, 11 years ago, the problem was there was no language for JSON, none at all. This is the period in which I was in the working group in WSBC. We are thinking of JSON support, and some of us tried for the discussions to spin off this JSONic out of xQuery. Back then, the feedback we got was, why do you even need a language for JSON? There's already JavaScript. Of course, the point that we're missing is that JavaScript is an imperative language. It's not functional and declarative, right? And then what happens in the 12 years that followed is just that everybody in the world had an epiphany that we need a language. So now that's no longer the problem. People know we need one. The problem is that there are too many. And what we need now is a market consolidation. What we need is for people to realize that we would need a standard, whatever it is, but a standard just like SQL on relational databases, a standard that everybody uses for querying collections of trees. I have no idea which one it's going to be. What I can tell you is that in the case of JSONic, this is based already on work by a standardization committee, but you cannot tell the future. Could be anything. But I do hope for the greater interest of the database community that the consolidation will happen and that we will have a language that people will use. Right? Yes?
It's the same case also with imperative languages?
That's actually a good question. I think that the need for a standardized language for data is even higher than for imperative languages. For imperative languages, I would say you typically have a limited ecosystem when you build software. You're within a company, you build the product. You do have efforts to grow across platforms, you know, with integration software like Snake and so on to go across platforms. You do have bridges between languages. But in the case of data, there is more communication on the queries that people use. You want to avoid vendor lock-in also. Maybe if you have a SQL query in a database system, you can switch the vendor and reuse queries at other places. In the case of W3C, right here, there is also the fact that you can share over the web these things. So it's kind of native to the web. So this is a lot about the interoperability. And the idea is that people can share their modules and share their code. But having said that, even though I told you my feeling that maybe for databases it's even more important, I think you do have a point that having interoperability for imperative languages is also something important. Right? And of course, things evolve. I mean, now it's Python, you know, the great language that everybody wants to use. In the 90s, it was Java. I mean, this keeps evolving. I think Julia right now is growing in popularity. Right. But yes, you have a good point. Okay. Something also that is evolving is that a lot more people start using UIs, user interfaces, instead of languages to directly click and produce reports, which is also something important. I think it's called the no-code in some startups, this approach. In some cases, I think it can definitely solve a few problems. Something else that is going on and that has increased in the previous years is the interaction with database systems with your voice. So there is Siri, Alexa, Cortana. I don't know if that one still exists, but you know the idea of having a voice assistant with which you're just speaking. And here, it's not something that is new in the collective imagination. If you consider series like Star Trek, I don't know if some of you watch it, but people talk to the computer. Right? This is the way people interact. And maybe in the future, more and more, we will move towards interaction with voices, and you no longer have to type any query. You can just ask what you want. So of course, it's a field. It needs natural language understanding. It's also taught at ETH. There's lectures about that. It's a whole ecosystem, but this is a bit also where things are going. Another thought is that data might become fully fungible in the sense that you can exchange data more easily. Fungibility is a bit like, when you consider water or electricity, it doesn't matter where it comes from, it's interchangeable. So this is something also in the crypto community that is discussed. I mean, now we have the non-fungible tokens that are quite the opposite, but there is basically something going on, and in particular, a convergence between value / data / money. So here it's highly speculative. We don't know where it's going to go, but there is something going on the high level in terms of data storage, and in particular, the storage of value. Of course, all of these things imply or have ethical consequences. Because if you want data to flow and to be available, then immediately you have the problem of privacy. How do you make sure people can control their data, that they are willing, that they give their consent for the data to be shared? And of course, this is the center of political discussions in the European Union, in the US. So there's also the cultural aspects to it, of course. And this is something that is being discussed. And that also means that when you have database systems and you write queries and look at data, you always need to keep the ethical aspects in mind and ask yourself, okay, am I doing a good thing? Does it have consequences? There are lectures at ETH on this. There is one called Big Data Law and Policy in the Humanities and Social Science departments that look at these kind of things. But this is, of course, something I do not teach in this lecture because it's a technical lecture, but it belongs to dealing with data. Something interesting as well, looking into the future that is going on, is the interaction between machine learning and databases. And here, the big question is, who will eat whom first? Will machine learning eat databases, or will databases eat machine learning? And the reason I'm saying that is that both directions make sense. There are people, here it is, who are replacing indices, these hash indices and B+3s that I showed you. When people at MIT, some of them come from ETH actually, but they are replacing these things with machine learning. Why don't we train the computer to learn the index? So here you get rid of these good old technologies of hash index and B-trees, and you just replace it with machine learning. What these people are doing is that they are trying to replace all the components of the database system with machine learning things. So in that case, it's really machine learning is eating databases. The opposite way, on the database side, people are also working on the integration of machine learning features within a database. Because you could consider that what is machine learning really from a relational table perspective? When you have a relational table, basically, every column is called a feature, and then you train a model of the feature, learning from a label column that has maybe a class, like this is a cat, this is a dog. And the machine learning algorithm is something that reads the features and gives you predictions of the labels. This totally fits in the relational model. And this is why some people are working on the integration of machine learning system with relational database systems, which is also a hot topic. So I hope it clarifies what I'm saying. Will ML eat DB or will DB eat ML first? We'll see what happens. Maybe it's going to be just a merger of the two. We'll see. Quantum computing is also a big thing. It's a bit uncertain now. We see at the high level. But quantum computers might start appearing. And here too, it might have consequences on database systems, because then we will consider, can we re-implement better than Spark or MapReduce something that leverages the quantum capabilities? So this is also an open question, but I think some people already started working on these things. Right. So for example, at Oxford, so Samson Abramsky is a professor at Oxford who is famous for working on topics like that. At some point, he even reformulated quantum theory in terms of relational databases. There's also a nice paper on that. Anyway, and this is more like, just a fun slide, that if you consider that the entire universe is a database, then in a way, the more we build and build and build and build, the more we actually turn the universe into a structured database. But it's just more a philosophical thought. Which brings us to the exam. So all of this, what we've been doing in the lecture, the slides, the recordings, the exercises, the theoretical exercises, practical exercises, the readings that I gave to you, the clicker questions. So all of that is basically what you need to work on to rehearse for the exam. I can tell you the following things regarding the exam. First, it's going to be a computer-based exam. What that means is there will be a room at ETH, so it's very likely to be either here on the in the main building, probably on the G floor, actually just up there in G1. Could also be in Earlycon in a building called ONA, where ETH has these super big computer rooms that are used for exams. It's a supervised environment, just like a regular exam. I mean, the TAs are here, you have a limited time and so on. And then on the computers, you have Moodle. So the same software that you use for the quizzes. Of course, the quizzes are not designed in the same way as exam questions, right? Because the exam is here to assess your knowledge. The quizzes are here to, provoke your thoughts and make you learn during the semester. But the environment is the same. It's going to be the good old model questions that you are already used to. So multiple choice, filling the boxes, and so on and so on. In addition to Moodle, you will have software installed on your computer. You have in particular 4 kinds of languages and assignments that you can specifically train on for the exam preparation. The first is PostgreSQL. Learn to write SQL query and query data that is sitting in a PostgreSQL database, like we've done in the exercises. This you may have at the exam. Second, PySpark. You might have a JSON file or whatever sitting on the machine, and then you need to write a PySpark code with transformations, actions, and so on. It's not going to be like you need to master Python, right? Just the PySpark that we've seen in the lecture to filter, map, flat map, and so on and so on. Then Spark SQL and data frames. Right, so if you want to write, also you have data lying on the machine as JSON or Parquet, and you need to write Spark SQL to query. If you prefer, you can also use data frame transformations, right? That's also something you can do. But basically, data frames / Spark SQL, and finally JSONic with RumbleDB. So these are the 4. All of these will be from Jupyter notebooks. On exam day, it will just work. Right? You'll arrive, you'll open the Jupyter notebook, it will be pre-populated, there will be sample queries and so on. It will just work. All you'll have to do is write your queries, and this is it. You won't have to install anything. Moreover, we'll share with you the exam environment. We'll share with you this Jupyter notebook that has a few samples query we'll give you ahead of the exam. And we'll also give you the data that we'll have on the exam. So you can even, before the exam, look at the data, see what it will be like, try to query it and so on, right? It's just to reduce the uncertainty that you know what to expect. And in the first years where we did that, we did not supply the data and so on. It went well as well, right? It wasn't a problem. But I think that it reduces your stress if we give you these things. So this is what we will do. And yes, so the exam is going to be 3 hours. The duration of the exam is something we try to control. I know that last year it was rather longer than usual, and the difficulty was perceived as higher. So what I did this year is that I capped the number of questions to 60, which is much lower than in previous exams. So the goal is that you should be done in less than 3 hours. So we hope that we'll see, right? We're going to try. We hope that with no more than 60 questions, the difficulty should be under control, right? Look at the time. We have the breakthrough, just 1 minute. Is there any questions? Yes?
What about the data sets that will be used in exams that will be already imported, for example, in a relational database or space, for example, locally on the computer?
Yes, so the question I'm repeating in Zoom for the people in Zoom. So will the data already be imported? The answer is yes. You will arrive in PostgreSQL, the data will already sit in the database. In the case of Spark, of course, as you know, there is no import, right? It's just a file that is there that you query. HBase, there is no HBase. That's just not a practical. There might be theoretical questions, but there is no installation of HBase, right? Does it answer your question?
Yes.
All right. something else, you won't have a cluster. All of this will just be on your laptop, not on your laptop, on the computer machine, just one machine. It's your job to not make it crash, of course, but there will be people to help. If it does, we can change the computer and so on. Shall we take a break? Let's take a break. 10 minutes, so we'll be back at 10 past 11, and then we do this big quiz together and celebrate the end of the semester. So I'll see you in 10 minutes. Thank you.